So this concept of pressure differences ultimately leads to the buoyant force. If you are in a fluid, say you jump into a swimming pool, you have a buoyant force acting on you. If you could take a scale and put it on the bottom of the swimming pool, it would read less with you in the water than if you were standing on the same scale outside the water. And that's because there's a buoyant force acting on you. Technically, there's a buoyant force on us right now because we've displaced some air. It's just that the density of air is so incredibly tiny that it's insignificant. You'd have to have a really, really big volume, say a hot air balloon, before that buoyant force becomes significant. So let's look at buoyancy. Buoyancy is a net upward force on an object because the object happens to be in a fluid. So an object in a pool would have a buoyant force acting on it. A hot air balloon in the air has a buoyant force acting on it. When we talk about buoyancy, we will want to remember Newton's second law. Net force is equal to mass times acceleration, because buoyancy is just a separate force. So when we look at what's happening to an object, we have overall what the force is. We have lots of sleepy people in here today. Lots of yawning. Buoyant force. The buoyant force is defined as the weight of the fluid displaced. Basically, if you're in a pool, you and the water cannot exist in the exact same location at the exact same time. It's impossible. Either the water's there or you are there. One or the other. So when you jump into the pool, the water that was there had to get out of the way. So the water level of the pool increases a little bit because the water moves out of your way. The buoyant force that acts on you is equal to the weight of the fluid that got out of the way. Okay? So weight. We know weight is mg. So if we can figure out the mass of the water that got out of the way, then we can certainly find the force, the weight of the water that got out of the way. Mass, density, times volume. So the buoyant force is equal to the density of your fluid, whatever the fluid is that you're in, times the volume that's actually in. If you're in the pool and you're standing up and you're only wet from the waist down, you don't use the volume of the whole object because you didn't displace your whole volume worth of water. You've only displaced the volume from your waist down. So this volume needs to be the volume in, the actual amount of volume that you moved. And G, of course, is just 9.8. This is our main equation for the force of buoyancy. It can be used in conjunction with Newton's second law, F equals ma, to find other forces or to find densities or volumes, anything along those lines.